sequential decision problems here we are discussing. So here we have seen that we have taken 4 × 3 environment as shown in the figure. So the robot has to start here. It can reach any of these two terminal states +1 and -1. So this is the transition model of the robot. So this is called intended direction. If the robot is moving in this direction, what is the probability assigned here is 0.8. The probability to the right angle to the intended direction is given as 0.2. So here 0.1 is the probability to move left side, and 0.1 is the probability to move the left side, and 0.1 is the probability that the robot to move right side. Okay, so this transition model, what is that gives? It gives the probability for the action. If it's moving up is the action. So what is the probability for moving one state to the other state is the probability is given as 0.8. So this transition model gives us the probability. And here we have seen that. So whenever what is the sequence that the robot will be reaching the terminal state is up, right is the sequential with which the robot will be reaching the terminal state. Okay. So here the robot should not take this fixed sequential state. If the robot is taking fixed sequential state, what happens? It will struck with the problem and it may not reach the goal state. That is why. So here it will not fix to this sequence always. Okay. So if it is taking this sequence, what is the probability that it will reaching the goal state is? It is given as 0.32776. It is the probability with which it is reaching the goal state. So if you see this probability, what is the percentage it will reach the goal state is only 32%. Okay. So here we have discussed what is transition model. The transition model is given as T of S A S dash. So by performing some action, what is the probability that the agent will move from state S to S dash? That is called transition model. This transition model gives us what? The probability of reaching the new state S dash from S by performing some action. Okay. And here this transition model depends on Markovian. What is Markovian here? What is the next state is S dash. The next state depends only on the current state. Okay, so this is called Markovian. So the transition model depends only on Markovian. Okay, so here we have discussed that whenever the agent is reaching the goal state, so there are two goals here. Whenever it is reaching this particular goal state, what is the reward the agent will be receiving? +1. Whenever the agent is reaching this particular goal state, the reward the agent will be receiving is -1. Okay. So whenever the agent is moving to other non-terminal states, okay, what is the reward it is reaching here? It is getting here is -0.04. Okay. So here the negative reward is given because the agent has to take the shortest path to reach the goal state. So it has to reach quickly to the goal state. That is why negative reward is given to the each non-terminal state. Okay. So what is the specification of sequential decision problem for fully observable environment is that? So this specification will be using Markovian transition model and additive rewards. Okay, what is that here it is doing? So how many steps it is taking to reach the goal state? Each and every step will be added to find out the total reward. Okay, so that is called additive reward. So these two are used here. That is Markovian transition model and additive reward is used to specify the sequential decision problem for fully observable environment. So this is called Markov decision process. So the Markov decision process will be denoted by 3 components. That is the initial state, that is the start state the agent will be starting, and the transition model. So what is the action the agent is taking from moving from one state to other state? What is the probability of the agent to move from one state to other state for given action is called transition model. And rewards, what is the reward here? How many steps it is taking to reach the goal state? For every step, there is a reward. Everything will be added together to find out the total reward to reach the goal state. Okay. So these are the three components we use to define Markov decision process. Okay. So any fixed action sequence, just now we have discussed right is the action sequence to reach the goal state. Okay. Any fixed action sequence won't solve the problem because the agent might end up in the state other than the goal state. So the agent may be entered into the state other than the goal state. That is why every time we don't use any fixed action sequence here. Okay. So what is the solution here is the solution will be specified that agent should do for any state that the agent might reach. Okay, whenever the agent is reaching particular state, the solution will be given such that what the agent should do in that particular state. Okay, so for example, here we have discussed this 4 plus 3 volume. For example, agent has reached this state. What is the state here? It is 1, 3. Once the agent has reached this state, so here the solution is given such that what is that agent has to do in that particular state, what action the agent has to take in that particular state will be given instead of giving total solution. So what is the solution for each and every state will be given. Okay. So that solution is called policy. So solution of that kind is called what? Policy. What is policy here? So here the solution must be specified at any particular state that the what the agent must do in that particular state. Okay. So what action the agent should take in that particular state. So that solution will be given to each agent. So the solution, that type of solution is called policy. Okay. So policy will be denoted by pi. Policy we usually denoted by pi. What is pi of s? Pi of s is the action. What is the action that is recommended at that particular state? Okay. Pi of s, I told you, once the agent is reaching particular state, so what is the solution given there? What action should be taken? Whether it should move up, right, left, like that. What action the agent has to take in that particular state will be given. Okay. So here only one action will be specified for that state. Okay. So that is called policy. Policy we denoted as okay. So policy will recommend what action to be taken at that particular state. Okay. So if the agent has a complete policy means for each and every state what action to be taken. The complete policy means what? For each and every state. So if it is at 1, 1, what action to be taken? If it is at 1, 2, what is the action it should be taken? Okay. So if the agent has complete policy, so no matter what outcome of any action. So if any action is taken, whatever outcome it may get, but agent will know what to do in that particular state. Understood? Okay. So if some action is performed, it is reaching particular state. Now agent no need to worry about this about the outcome because agent has complete policy. Complete policy means it knows action to be taken at every state. Okay. So if it is reaching any outcome also, it don't worry because it always know what to do in that state. Okay. So what to do next. Okay. So that is what complete policy. So each time a given policy is executed from the initial state. So from the initial state 1, 1, the policy will be executed. So the stochastic nature of the environment. So you know that what type of environment we have? Non-deterministic environment. Okay. So this stochastic nature of environment will lead to different environment history. Okay. Whenever the policy is executed, what happens? We will be getting different environment history. Okay. Different environmental history. So how do you measure the quality of policy here? So to measure the quality of policy, we have to find out what is the expected utility of possible environmental history. Because see here, whenever given policy, the policy will be given from the initial state. We told you policy is executed from executed starting from the initial state. Okay. So because of that, what is that we'll get? We will get different environmental history. Okay. So because of this, how do you measure the quality of policy? The quality of policy will be measured by measuring the expected value of environmental history. Okay, we have to measure the expected value of environmental history generated by that policy. Okay. So, what is optimal? What is policy? Policy will give you the solution for each and every state of the environment. Okay. What is optimal policy? Optimal policy is the policy that gives you highest expected value. So, how do you measure the quality of policy now? To measure the quality of policy, we are finding the expected utility of environmental history. Yes or no? We are finding expected utility of environmental history. Okay. So to obtain quality of policy, optimal policy, what is that we have to do? We have to find out the policy which gives highest expected utility. So that optimal policy we denote it as I star. I star is the symbol that we use to denote optimal policy. So optimal policy is the policy that gives highest expected utility. Okay. So given pi star optimal policy, so the agent decides what to do by consulting its current percept. So we know that what is the agent is depending on Markovian process. What is Markovian process? So to obtain what is the next state, it should know what is the current percept. It depends on the current input. Yes or no? Current percept, and this current percept tells the current state. What is the current state of the environment? Then executing the action. What is the action specified by pi star s? Okay. So pi star s is the optimum policy. That is also gives you what is the action to be taken in the current state. Okay. How do you get current state? By just getting the current percept. Current percept will give you what? The current state of the environment. Okay, once we get the current state of the environment, the action will be taken on the current state. What is the action will be taken on the current state? Is pi star s is the action taken on the current state. Okay. So, what is the optimal policy for figure 1 we have seen now, students? Figure 1 is that this is the start state, these are the terminal states. Okay. For figure 1, what is the optimal policy is that this is the optimal policy. Okay. So, if the agent is here, see here, student, if the agent is here, the agent has to go these steps to reach +1. Okay. So, for example, if the agent is here, agent is at 4,1. See here, all of you, the agent here is at 4,1. Then what are the steps the agent will take to reach the state +1 is, these are the steps agent will take to reach +1. Okay. So there is one more possibility that if agent is here, it can also go in this way to reach the +1. Okay. This is the optimal policy for the 4+3 world we have discussed. No? Okay. So, what is figure 2, 2,A is the optimal policy because the cost of taking step. So each and every step is very less. What is the reward for each and every non-terminal state? Is minus 0.04 is the reward for each non-terminal state. So that reward is very small compared to falling into this risky state. What is the risk? -1 is very high value compared to the reward of each and every state. That is why the agent don't want to go to this -1 state. Agent will always want to reach +1 state. Okay. So that is why the optimum policy is given like this. Okay. So So that is why sometimes it is taking this long route to reach +1 instead of going to -1. Okay. So because it should have maximum utility value for environmental history. Okay. So here the balance of risk and reward changes depends on the value of R of S. What is the reward for non-terminal states depending on R of S. What is R of S? The reward for non-terminal states. In this particular example, what is the reward for non-terminal states is -0.04. For terminal states, the reward is +1 and -1. Okay. So the agent don't want the negative value -1. So that is why the agent will always want to reach the terminal state which is having the reward of +1. Okay. That is why the agent will be avoiding this -1. The agent will always avoid this -1. Okay. So the balance of risk and reward changes us depends on what the value of R of S depends on value of R of S. Risk and reward values will be changed. Okay. So the figure here 2B here you see here the first figure. This shows that what is the reward R of S for less than or equal to the reward value R of S is less than or equal to -1.2684. So here this will give you optimal policy for different values of rewards now. So if reward is less than or equal to -1.6284, it means that the agent will always take the shortest path to reach the terminal state. So it does not worry about whether it is +1 or -1. Okay, it wants to reach the terminal state in shortest path. Okay, so that is why see here students, if the agent is at this location, so this location is 4,1, it will reach the terminal state in the shortest path. If the agent is here, it will be reaching the terminal state here like this. Okay, so the agent has to reach the terminal state in the shortest path. So the reward you see is negative value. The reward is -1.6284. It is the negative value. Okay, so if the reward is between these two, so what is the agent direction? The agent don't want to reach -1 at all. Don't want to reach -1. Okay. So but it is taking the shortest path to reach +1. The agent will be always taking shortest path to reach +1. See here, this is the shortest path to reach +1. So if the agent is here, it will be taking the shortest path like this. So it can also take this path to reach +1. The agent never wants to end at -1. Don't want to terminate at -1. That is the second case. The third case is that so here there is a risk of falling into -1. Since the agent is taking this road, so there is a risk of reaching -1 here. Okay. So in the third case, the agent wants to avoid the risk of reaching -1. That is why. So here you see at the -1, the directions are always away from -1. The agent will be having the direction always away from -1. What is this indicates? Agent never wants to never wants to take the risk of entering -1. So in this particular case now, there is a risk of, once it is reaching here, it may enter into this. There is a risk of entering -1. So this risk of entering -1 should be avoided. So that will be avoided by using the third case here. So in the third case, what is the reward? The reward is in this range. Okay. Now in the fourth case, the agent never wants to enter into the terminal state. See here, the directions in 4,1 and 3,2 and 3,3. The directions are given such like this, so that the agent never enters into the terminal state. Here it can have any directions model. Here the stars are given. So here it can have any directions, but agent is never entering the terminal state. Okay. So what is that here? If you observe, The reward in these three cases is finite, whereas in this case it is infinite. Okay. So if the reward is finite, then it is called proper rewards. Okay. So these are the three examples for proper policy. Proper policy means what? The reward value is finite. Okay. So this is the example for improper policy. So because the reward value is infinite.